Optimum efficiency is a key requirement for any combustion process. To achieve the ideal balance, the level of excess air must be sufficient to burn all the fuel, but not too much to reduce efficiency or increase NOx production. If too little air is applied, the flue gases will contain high levels of carbon monoxide, soot and smoke, increasing the risk of pollution and potentially affecting safety. The presence of unburned fuel is symptomatic of an inefficient combustion process, as some of the energy in the fuel is effectively being wasted. It can also pose a risk to safety. If the unburned fuel is ignited, then an explosion could occur, with potentially disastrous consequences. Two gases that provide a particularly good indicator for combustion optimization are oxygen and carbon monoxide. Accounting for approximately 21% of the composition of atmospheric air, oxygen provides an excellent indicator for regulating excess air. However, maintaining the correct level of excess air for combustion can be complicated by variations in the fuel and the air. Factors including atmospheric pressure and humidity, changes in the heating value of the fuel, and the performance of the boiler plant itself. Measuring for carbon monoxide provides an ideal means of compensating for these variations. Carbon monoxide levels will start to increase when the amount of oxygen is insufficient to allow complete combustion. By continuously balancing the two measurements against each other, it's possible to achieve and maintain the correct amount of excess air for optimum combustion, regardless of any of the variations mentioned earlier. ABB's AZ40 Oxygen and Combustibles Analyser continuously samples and analyses combustion waste gases to determine the levels of excess air and unburned fuel. Featuring a close-coupled extractive design, the AZ40 uses a sensor assembly mounted on the process wall, with the probe and filter assembly extending into the process gas stream. The sample is extracted from the process and fed through the sensor head using an air-powered ejector. The COE sensor consists of an inert-coated reference element and a catalyst-coated active element. Both elements are resistance temperature detectors, or RTD. As the sample gases flow by the sensor, the combustible gases oxidize on the surface of the active element. The heat generated by the oxidation causes a temperature difference between the active and the reference elements. This temperature difference produces a resistance relationship between the two elements that is directly proportional to the concentration of combustibles in the sample gases. Oxygen analysis is carried out by an industry-standard zirconium oxide cell. Zirconium oxide sensor technology produces a reading of the net oxygen remaining after the combustion of all the available combustible gases. The sensor consists of a thin piece of zirconium material. A supply of air is applied to one face of the sensor as a reference gas. The process gas being measured is applied on the opposite face. When the concentration of oxygen is equal on each side, migration of the oxygen ions through the zirconia is zero. When concentrations differ, migration of the oxygen ions will increase as they try to re-establish equilibrium. The reaction at the two electrodes will differ, generating a corresponding potential difference. Using an appropriate device, this difference can be measured to produce a percentage oxygen concentration reading. For more information about ABB's AZ Analyser range, contact your local sales representative or visit www.abb.com/measurement.